Alright, let's start lesson 4. So in this lesson is the process control modes of control. How does the controller respond to any changes in the system? And there's specific setups and amplifiers and all that. We're going to talk about basically the main setup and how they work. So a little bit more on capacitance. There's two components to capacitance. There's capacity, a condition that refers to the ability to store energy or material in the system. So some systems have a large capacity, some systems have a small capacity. And then remember, this deals with inertia too. The higher the capacity to store energy or material in the system, the slower the system is going to respond to changes. And then resistance is a part of capacitance. Anything that tends to oppose a transfer of energy or material when a process change occurs. And why this is important, because when we get into modes of control and just system control overall, the rate of change of control, how quickly the system responds to changes when the controller changes the output. Say it's trying to change a temperature, and if the temperature changes really slow because there's things that impede the inertia or the change in the system, then you've got to take that into account, and then in turn you have to set up a controller so it responds correctly, so the system doesn't hunt. So there's a lot of factors in how you set up and control the system, and what kind of controller you use. And so basically, capacitance is just the time lag of the system. Also think of capacitance, if you remember inertia, is the system going to change quickly? Does it have a small inertia? Or is the system going to take a long time to change? And systems, their capacitance may change over time. Say you've got a boiler, a steam generator with a boiler. Initially when it's cold, it's going to take a long time to heat it up, so its capacitance is very large. The temperature change will be very slow. Once it's up to temperature, temperature changes can be very rapid, and so you could vary the burner or the fuel to the burner quick, a little bit to get a large change in temperature, or a quick change in temperature. So the lesson objectives, here's what we're going to cover. We're going to learn the different modes of control, and there's just a few set modes, and these are consistent across the industry. There's on-off, the simplest. Either there's an error and then it's gone, there's an error then it's gone. Proportional, integral, and then you have proportional integral, which gives you the best of both. But sometimes proportional and integral don't work, so you need a derivative. You may have a proportional and derivative, or you may have all three. Not all systems need all three. Obviously, the most complex systems, where you want to control hunting, rate of change, and all that, is a proportional, or what they call PID. Don't confuse it with PID, the type of mechanical drawing of PG. So a simple process control diagram again. The main thing we focus on is the measured output, our set point of reference, and then the error. And then the controller is what modes of control is. That's where we set all this. This is where we work all this. Of course, the controller is a central part of the automation. So design and maintain a given process at a predetermined value. And you can do this by, we've talked about pneumatic, electronic, electrical, and mechanical energy and systems. Pumps, valves, motors, electromagnetic valves, whatever method we need to use, air valves, pneumatic. So the controller maintains process output through two signals. And so it's the system set point of reference and the output feedback, which is the measured output from whatever your sensor is. So last time we talked about this sensor, the input device. What do you measure in the system? What are you maintaining? and what kind of instrument you use, and then how is that instrument output converted to a signal that can be used for your reference and to your controller. So let's start going through the control modes. First is on-off, and we will classify this as a discontinuous mode. Continuous mode we'll talk about in proportional, and on-off is the only discontinuous mode. Obviously, it's the simplest controller setup and operation. So it's either on or it's off, and there's no intermediate operation. Kind of a good example is your home's thermostat. You set a temperature, and it maintains that temperature. So it's either on or it's off. So the system has one set point. And in an on-off system, to prevent continuous on-off operation, the set point has a differential or deadband. So you may set the temperature, like I set the temperature in our house at like 68, 69, and that maintains the house plenty warm. So, but if the house heats up to 69, then it may not, the thermostat doesn't actually kick on until it goes back down to 67, so that's a deadband. And that's just so the system doesn't cycle on and off. Most on-off systems have a deadband, like a governor pump that maintains the oil level and pressure in the system, in the accumulator. If the level gets too low, pump comes on, and then it goes up and it stops at a certain level, and then it doesn't come back on until maybe it comes down an inch or two. So just a picture showing this. I mean, this is a reference to our time and the set point, and so this is the error signal. It's either on or off. And so this may represent the deadband. So you may have a set point of 70 degrees, you have an upper deadband of 71, lower of 69. All right, enough with on-off. We see on-off a lot, though. A lot has to do in our home. Continuing on, proportional controller. This is classified as a continuous mode. The control element can be adjusted to any value between full open or closed. Sorry, I've got a car going by outside, a little noisy. One of those Subarus with the loud mufflers. The value is determined by the ratio of the set point input and the actual process value of the system. And then it's converted to a signal that equates to the same percentage of the system operating range and controlled variable input to the system. All this is saying is just the signal is proportional to the change in the system. To put it in very simplified mathematical terms, and these you see, if you go online and just put in process control PICs in Google, you'll see a lot of papers and presentations on systems. And you'll see a lot of formulas with differentials and derivatives, but they all center around your voltage output, which is signal output, is based on K sub B and V sub B, which is the error and then the set point signal. So V out is controller output, and then KP is the proportional gain, controller gain. And then V is the error signal, your set point minus this is your signal from your output sensor. We normally set this up as a linear or close to linear function, as opposed to like an exponential where it's increasing. The rate of change increases or decreases. Linear means it's just a constant rate of change. And based on the span of the control. So where the valve is fully open. And I'll explain this in a minute too. Some important features of proportional control. Make sure you set the system up right. So this is just a simple diagram. A very simple, not diagram, but a simple system where it's a a level control system. So once this is your error, so there can be a dead band. Once the level goes down about here, then your system comes up. Your valve opens. This looks like it's proportional control, so the lower the level, you got some flow, so the higher the flow means the lower the level comes on. So the proportional control is the inlet equals the outlet. And you also got to make sure that whatever your system control is can actually match the output. So if you have a valve here and a flow that when this is fully opened can't maintain the flow because there's not enough inflow to match the outflow, then your proportional control system doesn't work. Same as if you reach your set point, your level back up, but the valve is still filling, then your system control, your proportional control does not work. Your motor control is not working. I hope that makes sense. So I want to make sure that your lower and your upper limits match the system parameters so it controls the system within the variables that it needs to. Proportional control. Just some things to think about. It works well where process changes are small and slow. Disadvantages: does not respond well to large or long-term changes in the process system. A change or disturbance will not let the process return to its exact original value. That's where integral comes in. And this is known as offset. So a proportional controller the offset can change. It can maintain a higher level, a lower level, it all depends. And you don't want that in a lot of systems. And the offset may or may not be okay in the process system operations setup. And I talked about this before, the range must be correctly set so that the upper and lower limits maintain the system properly. And then proportional control gives you a big problem with hunting, because you'll reach your limit, but the controller is still working, and say it's still providing water flow in, so the level will get too high, then the controller will overshoot and come back down and shut down, and then the level gets too low, and then basically just hunts. Too high, too low, too high, too low, and eventually it might level out, but then you might get another change, which now you've got another proportional control process where it keeps hunting. So the system may, if the controller doesn't work right, may never return to a steady state value. So integral control. This is another channel you don't see integral by itself, but so we're going to talk about it just about integral control, and then we'll talk about it combined with proportional integral. So to minimize or eliminate offset, the rate of change of the controller is proportional to the system error signal by magnitude and duration. And bear with me, I'm doing some technical definitions here, but then we'll show it. So as long as there's an error, the controller will continue to change the output. When the system error is 0, the integral controller will maintain the output at the new value until another error occurs. So that is what we mean by offset. So you may get a change in the output value. It may maintain at a new level or new pressure. So just another formula maybe this makes sense to you to represent controller output voltage. That's always the V out. Time rate of change. So in proportional, there's no time rate of change. It's just if you have an error signal, the signal matches the error signal. Here you factor in the rate of change of time. So over time, you want to eliminate that error signal. Ki is the integration constant, and then VE is the error voltage. So here you can see you've got, here's steady state is 0. You get a big error, and you can see the slope on this is steep. And you got this right here, and now the error goes lower, so the slope comes a little bit off. Whoops, sorry, I'm going back. And then here the error gets less, the error signal, and it doesn't look like it, but the slope would be a little bit less. And here the error signal is gone. So now you've got a new output level. Steady state. Now you have a negative error, so that has a certain slope, and the error goes away. It's now a steady state. Now you've got a positive error. And the positive negative is just a reference point to 0, or the horizontal axis. And so you get this integral. And then the error goes away, and you get steady state again. So proportional plus integral control. So integral control does not respond well to transients. It's too slow. But it does respond well to long-term or steady-state errors. Proportional control responds well to transients, but it cannot reduce offset to 0. So with proportional and integral, you're combining best of both. It's a good process for controlling large load changes and frequent set point adjustments. So here I just brought this up. Process variable set point error amplifier. You get a signal that goes to a proportional amplifier and an integral amplifier. And so you may have an inverting sum amplifier, which means that if you have a positive error signal, you want to provide a inverted or negative error summing signal to bring the error back down. Here you could possibly have an output differential amplifier. So there's a lot of different variations and control systems you can set up with proportional and integral, well, with everything. So the third type of control is derivative. And all derivative is just a math term for rate of change. So, and we've talked about this before, process controllers often have an inertia or hysteresis problem. Well, I don't know if maybe it's not right to say the process controller. It's the system and the process controller have a inertia or hysteresis, not problem, but it's just the way that the characteristics of the system. So to overcome inertia issues with the process system, often larger than normal input signals are used. So you have a large, remember inertia is a body at change, a body moving stays in motion, a body at rest stays at rest. So basically this is changing a system. There's going to be some type of inertia where a system doesn't want to initially change. And then it'll slowly start changing until it reaches new steady state. So to prevent system oscillations, or hunting, we use a controller that allows large initial signal, and then it quickly drops off with time. So you get a large signal, you get the process moving, you get the system changing, and then you drop off that signal over time towards 0. And the system approaches this new steady state. So a differentiator works in proportion to the rate of change of the error signal. If the error signal is changing really fast, the differential or derivative control signal is going to be very large. If it's moving very slow, it may be the derivative control signal may be very small, or it may just have a lag time where it doesn't even start until you get a certain error control level. So here you've got the error signal. You get a large spike in the voltage. You can see the controller this is just straight derivative. Peaks, overcomes the inertia of the system, gets it moving, and then it comes back down here. And now you've got some steady state new level, and then you can see right here, steady state new level here, not here. And then you get a drop in the error signal, or a negative error signal. So now you get a negative spike in the control output, and then that signal drops off. And now you have a new steady state. And you can see you just keep going here. So you get another spike from this. See, this is not a rapid change. It's more like a slow increase in the error. So that kind of shows you how, with the change in the error signal, how the controller, the derivative controller, will output that. So if the signal's not large, the controller output may change not as rapidly, or may just change to a new level and be steady state. I hope that makes sense. Proportional plus derivative. I mean, you guessed it, the final slides will be proportional, proportional, integral, and derivative, PID. It's responsive to system changes and the rate of change of the error signal, or the rate of change of the system. It maintains the current level as long as the rate of change of the system stays the same. So if a system's changing at a constant rate, the error signal is constant. Anticipates system changes. So it's good for processes that have a sudden load change. So here's a really good example now. So you've got this. This is not an instantaneous error signal. It's a ramping up error signal. So you'll get an initial see, the D is for derivative. So you get this is the derivative part of the control signal, then proportional increase. Derivative drops off. Now you've got a constant control output and a constant error signal. Now it drops off proportionally. So that's the proportional part here again. 0, 0, and then of course the reverse in the negative direction. So proportional, integrated, and derivative. Obviously, it's the benefits of all three types of controllers. The proportional part responds to system transients. Integral is output rate of change is proportional to the time the error signal is present. So remember that. So integral responds to how long the error signal is there. So proportional is just strictly the response to system transients. The larger the system transient, the larger the proportional signal. And then derivatives responds to the rate of change in the error signal. So if it's a large rate of change in the error, then the derivative response is going to be large. So the integral is time, derivative is rate of change, and proportional is magnitude. So you factor all those in. Hopefully that kind of puts everything in perspective. So here's what you may see. This is an electronic circuit, but I could have probably just drawn a simpler diagram. So here you have your error signal, and that goes to your proportional, integral, and derivative amplifiers. And then those signals, depending on what's going on, go to a summing amp. And so this graph will show it. So let's say you have, the reference is negative, so you have a negative error, constant, and then it goes away. So your proportional output will go in the positive direction, which is inverting, so it wants to overcome the negative error, and bring it back positive. same magnitude. So it just looks the same except it's the opposite. So as long as this error signal is here, you see the integral output is there and keeps increasing. And if the error signal would stay there, the integral part would just keep increasing. Until finally the error signal went away, and then the integral part would drop off. The derivative output, this is a big step change. So it says, oh, hey, this is changing really fast. We jump it up, and then you bring the signal down. This is an arbitrary level. And you bring the signal down, and then it goes away, okay, negative, and then bring the signal back up. So the overall controller signal would look like this. So this would be the controller output. And the controller output would be a combination of, if you look, it's kind of the negative of the derivative, but it's magnified. Because you take that derivative output, and then you add in the integral and the proportional signals. Same here. You take that derivative drop off, you add in the integral and proportional signals. So that's all I have for modes of control. Hope this makes sense. And next up is lesson 5. Thanks.